Okay, welcome. This is the first colloquium this semester. We're very pleased to have one of our own, Radwan Tajeddine. That's correct. Radwan was educated in Paris, working with Sebastian Valerie. Okay. So for the last 3 or 4 years, he has been working here with Joe Burns and Phil Nicholson. Dynamics problems, but involving both interior dynamics of satellites, but also rings and other subjects. So today we're going to talk about how do we find ocean.
Thank you very much. Thank you all for coming. It's a pleasure to be here, and I'm also very honored to be selected among the top 10. It honors me also to know how much the department values my research and work, and I really appreciate that. So I'm mostly specialized in Cassini data analysis and application to study the interior of moons, Enceladus and Mimas, and also the study of the dynamics of the rings of Saturn. So today I would like to talk about one of the fields I'm specialized in. It's finding oceans. And so far we have a few oceans found in the solar system. Before I go on, I just want to make a quick comment on this picture and why am I putting this picture. It's actually, there's a story for it. When I told my wife I want to give a talk about how to find an ocean, she said, well, isn't this how you find an ocean? And I found it cute and I decided to put it as a background. So why should we care about finding oceans in the solar system? First of all, it teaches about the heating history inside the objects we found oceans in. It also tells us about the different geophysical processes that's happening inside that could explain the surface geology we're observing. And also because we need to look at different heating processes and the sources of heating, it tells us about the orbital evolution and the history of the moon. Of course, when I talk about oceans, I mean oceans in icy satellites, which is the only other place where we found water besides Earth. Well, there's Mars, but let's stay on the icy satellites. And of course, the most important reason, and this applies not only in our field, but also for the general public, is finding life. We only have one data point for life, is that life needs water. And so finding life first requires finding water. And so there are multiple objects or satellites in the solar system that have been confirmed to have oceans. By the way, do you see these words here, or is it too dark? I can do it. Okay.
You might want to kill us. Hard to see.
Is it better? Okay. So we have the oceans have been confirmed in the Galilean moons, Europa, Ganymede, Callisto, and with the Cassini mission inside Titan and Enceladus. Of course, when you look here, you can clearly see the elephant in the room, or more like the ant in the room. It's Enceladus. You know, it was believed that only big satellites could have oceans, but then Enceladus proved us wrong, and it also has a global ocean. You know, if there's one thing we learned from Enceladus, the ocean is that size doesn't matter. There are other candidates for having internal oceans. There are the Mimas and Dione in the system of Saturn, Triton, the moon of Neptune, and Pluto. But I'm going to be mostly focusing on the ones that have been confirmed. Okay, so just a quick, make sure everyone is on the same page. When I say a satellite, I mean a natural satellite, okay, not a moon. So that's for the non-astronomers in the room. I don't mean the artificial satellites. Those are fake. So there are different techniques that were used to find oceans inside those objects. For the Galilean system, it was mainly the magnetic induction. For Titan, it was mostly through gravity and tidal stretching. And for Enceladus, it was the libration, which is a rotational parameter. So before looking for oceans all over the solar system, we need to look for hints right? So we don't just go and look randomly all over the system. So there are three different hints you should look for. First of all, in order to form an ocean inside an icy satellite, you need to melt the ice, which means that you need a heating source. So the first source of heating is radioactive decay. There's also another source of heating, that's the tidal heating, and that's even stronger with orbital resonances. And finally, you can look at the geological activity on surface and tell if it's an object of interest. So let me start with the first one, and that's the radioactive decay. So this is a table of the elements that are the most dominant elements in terms of radioactive decay and energy production in the solar system. They are classified in order of half-life of the decay. And so the aluminum-26, as you can notice, it's very short half-life. So most of its energy is produced very early in the solar system. And this element is very important in terms of differentiation. So the heaviest material will go inside, and the less heavy stay on the top layers. But after the system runs out of aluminum, then you have the other isotopes like uranium, potassium, and thorium that take the role in heating those objects. Those elements mostly exist in the rocky parts of the satellites. So the larger the rock fraction inside the satellite, the more energy is being produced. And also, the larger the rocky core is, the more energy is preserved over the time scale of the age of the solar system. So basically, whenever you want to look for oceans, you should look for first if they have a large rock fraction. This is a plot that puts all the icy satellites and Pluto in terms of silicate fraction, so that's the rock, and the size represents the size. So when you look at here, you can already make a clear distinction, or just make a, filter out the objects that are of interest. So you have, for instance, the objects that are the biggest and with the largest silicate fraction would be, you have all the Galilean moons, so you have Callisto, Europa, Io, and Ganymede over here. You have Triton, the moon of Neptune, and you have Titan, also the moon of Saturn, and Pluto over here. So these, just by looking at this plot, you can already classify which are the objects that have more energy production inside. The other source of energy or heating is tidal heating. So how does this work? We all know that from any object that rotates, the centrifugal forces tend to make it ablaze. However, when a satellite is in synchronous rotation, which means that it's always showing the same phase towards the planet, then the tidal potential from the planet on one side will be stronger than the other side. So this will tend to stretch the object and make it more elongated. Now, when the object is closer to the planet, the difference between those forces are even stronger, so the object will become even more elongated. Now, imagine if the object is going back and forth. So if it has an eccentricity, then it gets closer at some point at periapse, and then gets further away at apoapse. So when it goes back and forth, it will be stretching back and forth, and friction inside will create heat and will melt the ice. So in order to give eccentricity to the orbits, one of the ways is resonances. And how do resonances work? So imagine if you have a moon with one orbital period and another moon with two orbital periods. 2 days, sorry. 1 day and 2 days. So that's a 2-to-1 resonance, which means that this moon goes does 2 orbits around the planet. This moon does 1 orbit around the planet, then they get back to the same location. So as they orbit, they run into conjunction. At this point, both moons perturb each other's eccentricities. So instead of being on a circular orbit, they will go on an eccentric orbit. So as they orbit around the planet, they'll continue orbiting, and then they run again into conjunction. And then the eccentricity is perturbed even more. So in this case, I mean, if those moons are always in resonance, the eccentricity will go very high, and then the orbits will become hyperbolic, and then they will leave the system. So you need something that damps this eccentricity. And what damps the eccentricity is the tidal heating. So because each moon is getting closer and farther from the planet, it's heating up and it's damping this eccentricity. So basically you have this balance between the resonance that is increasing the eccentricity, and then the tidal heating that is decreasing it. And so as long as the moon is in resonance with another moon, it will continue heating through tides until it exits the resonance, and then the eccentricity is damped. So these are a few examples, or these are the examples of resonances for moons in the solar system. The most known one is the Laplace resonance between Io, Europa, and Ganymede around Jupiter, and those go as 4 to 1. You will also have the Enceladus and Dione around Saturn. Those are in 2 to 1 resonance. There's also Mimas and Tethys that are in 4 to 2 resonance, which is the same as 2 to 1, but it's just a terminology to say that it's an inclination type, so instead of exciting the eccentricity, it will be exciting the inclination. And there's also Titan and Hyperion also around Saturn. So this is the equation for the heat, the rate of energy dissipation inside the satellite. So what matters is that it depends on the eccentricity squared over the semi-major axis to 15 halves. So the dominant parameter here is really the distance. Of course, if you have zero eccentricity, then you won't have any heating. But what matters the most is the distance. So the closer the object is to the planet, the more heating it is producing through tides. And this was actually a very beautiful prediction that was made by Thiele et al. in '79, when they predicted that Io will be, before the arrival of Voyager, they predicted that Io is going to be melting, and they also predicted some volcanism on the surface. And so this paper was published a week before the arrival of Voyager, and Voyager gets there, and boom, you have these beautiful volcanoes popping from Io. And so for me, this is one of the most beautiful predictions in the solar system. Okay, now this brings me to the next part, and that's looking for signs on the surface. So that's the signs for geological activity. And so when Voyager was a very important mission because it gave us the first images of how those moons look like. So we could already, by looking at surfaces, start classifying them as which the objects are more interesting than others in terms of internal ocean. So basically, when you talk of geological activity, you mean resurfacing. So the more crater the moon is, the less it is active, the less heat is being produced inside. The more resurfaced is, the more there is craters that are being erased, then the more heat is being produced from the inside. So the first looks just, you can tell that Europa is very interesting. There's a lot of resurfacing. Ganymede is a mix between both cratering and resurfacing. Callisto appeared to be not that interesting just from the surface, because it was mostly just craters, with all my respect to those who work on craters, but this is just for the purpose of oceans. Enceladus appeared to have some craters, but also some resurfaced terrains. Dione had mostly fractures on surface, and of course, craters. Titan, back then, we couldn't really see anything because it has a very thick atmosphere. So the camera of Voyager didn't really allow us to make any conclusions. Hyperion just appeared to be one piece of rock, or ice in this case. Mimas and Tethys also are heavily cratered, and there's a very limited amount of heating or resurfacing. Triton appeared to be very, very resurfaced. I don't think we found any crater on Triton. I don't know if there's any Triton people here, but it appeared very, very resurfaced, which means it's a very interesting object in terms of ocean search. Later on, Galileo went to the system of Jupiter, and it took closer looks at the surfaces. These are the chaos terrains on Europa that show you have these ice sheets that are being broken apart. There are different hypotheses to explain those. Some suggest that the ocean is very close to the surface, which almost making those ice sheets float on the ocean. And there are others that actually suggest that it's a very thick layer of ice, and it's really just convection and plume production from beneath. There's one of the people who favored, or one of the movies who actually favored this thin shell is Europa Report. Have any of you seen this movie? Yeah. Basically, if you land there, you get eaten by a giant squid who breaks the ice and eats you. So, there are also other signs like fractures and domes that show a lot of tectonism going on in Europa. This is an image of the surface of Ganymede, and you can clearly see signs of expansional terrain. So there is tectonism on Ganymede. Later on, Cassini arrived to the system of Saturn, and it showed these. The radar of Cassini showed these beautiful images of lakes on Titan. However, these lakes are methane, not water. And it also showed dunes on Titan. So Titan is really, in the solar system, is one of the closest relatives of Earth in terms of geological processes on surface. However, on Titan, most of the geological or the resurfacing is really exogenic in a sense that it's in the atmosphere, not a sign from the internal heating. And of course, Enceladus with its wonderful plumes from the South Pole, and these are erupted from these cracks in the South Pole of Enceladus, and so this pushed Enceladus all the way up to the objects of interest. So now we can just, without really doing any detection for oceans, we can already classify which are the objects of interest. And so now, what are the techniques that were used to find oceans inside those moons? So I'm going to start first by talking about the moons of Jupiter and the magnetic induction. So just a quick reminder for everyone. This is my talented drawing here. So imagine if you have a conductive wire on a loop, okay, and then you pass a magnetic field through it. If the magnetic field is constant, then nothing will happen. However, if the magnetic field is increasing, then the wire will produce a current in it so that it opposes to the increase of the magnetic field. If the magnetic field is decreasing, then the current will go in the other direction to oppose the decrease. So magnetic induction really works like human societies in a sense that whenever you create a change, you should expect resistance to it. So Jupiter has the magnetic dipole of Jupiter is similar to Earth in a way that it's tilted from the spin axis. So if depending on where you are, where the moon is in the magnetic field of Jupiter, it will be sensing the magnetic field differently. This is a nice Hubble Space Telescope image of Jupiter's aurora that show that they're tilted from the North Pole. It's a nice direct evidence of this tilt. So if you're, for example, on Europa, the Jupiter spins faster than the orbital period, or than the orbit of Europa. So what happens is that this is a movie that shows how the magnetic field of Jupiter varies around Europa. Here is Europa, and you can see it's going up and down as the planet is rotating. So in this case, if there's any conductive layer inside the moon, it would be expected to resist to this change and producing an induced magnetic field. So this is how the magnetic field around of Jupiter looks at the orbit of Europa. So this is just a prediction, not a measurement. And you can see it's varying in the radial component and in the azimuthal component. The polar component doesn't vary as much, although it is the strongest one. So what matters is not the strength of the field; it's really the variability of the field. And this is around Callisto, and you would expect something similar around Ganymede. I didn't find a plot for it. So as Galileo was flying by Europa, so these are different flybys, and this is in the geometry of Europa. So this is here. You have the magnetic field as a function of time, and as Galileo was flying near Europa, it was first measuring the magnetic field of Jupiter because it was still far, and once it got here, the magnetic field of Jupiter got disturbed. So this is the magnetic field of Jupiter, and this is the detected signal, and it's the same happened in all the other components. So it was interpreted that there is a magnetic induction coming in from Europa. So where does the induction come from? Well, you need a conductive layer. Ice is not really conductive. At least it's not conductive to this level. Rock is not conductive. So you have two options: either iron, which is all the way in the deep interior, or an ocean, a salty ocean, because just pure water is not really conductive. So you need a salty ocean. And this is what I was suggesting, that right beneath the ice there is a conductive layer of salty liquid water. And then they found that iron actually is too small inside the planet or inside the satellite to produce such a strong signature of magnetic induction. So it was concluded that it is an ocean, and the thickness of the shell is about is less than 100 kilometers. So there are many models that suggest different depth for the ocean. So basically, Europa is made out of an iron core, a rocky mantle, an ocean, and then an icy shell. The same was applied for Callisto, and the same disturbances were found in Callisto. So this led to the same conclusion, that Callisto has an internal ocean. However, gravity data, so as Galileo was flying by Callisto, it detected the gravity signature of the satellite. And from there, you can also conclude or make conclusions on the interior of the moon. So even though Callisto has an ocean, the interior is not completely differentiated. So the interior is really more a mix of rock, ice, and metal. And what's interesting about Callisto is that Callisto is not being tidally heated. It's not in resonance with any of the other moons. It's just on its own. So most of the heating coming in Callisto is really coming from the remnant radioactive material in its interior. So this radioactive material was enough to melt the ice, but it wasn't enough to differentiate the different layers. Ganymede is a very interesting case. So this is the measurements of Galileo as it was orbiting Jupiter, and then it was getting near Ganymede. It detected a signature of the disturbance in the magnetic field. However, the disturbance is stronger than the background field. So usually when you talk of magnetic induction, it should resist to the magnetic field, but it shouldn't be stronger. So the conclusion that was made for Ganymede, that is, Ganymede actually has its own magnetic field. And so Ganymede is the only moon in the solar system so far that has its own magnetic field. For an object to have its own magnetic field, it needs you need convection inside. Of course, you would argue that, well, there is convection in the water, in the liquid water, but then why didn't you find magnetic fields around other moons that have subsurface oceans? So the most accepted model for the interior of Ganymede is that it has a partially molten iron core, and the convection is really happening in the iron core, and this is what's producing making Ganymede has its own magnetic field. So far, just from this detection, you can't conclude that Ganymede has a subsurface ocean because we didn't find any induction. However, Galileo did more flybys around Ganymede, and it managed to measure the magnetic pole, the magnetic moments of Ganymede to the quadrupole level. And so at this moment, the magnetic induction was found, was detected, and then an ocean was confirmed. For Ganymede, it's actually a very interesting case in terms of the ocean because it's the largest moon in the solar system. So it's so big that in the deep interior, the pressure is so high that it increases the melting temperature of ice. So the ocean is sandwiched between two layers of ice. So it's not in contact with rock. And this is an important question for life, because usually life is, for so far, I mean, it's not like we know so much about how life can develop, but it's more favorable for life to develop when water is in contact with rock. And then it has a rocky mantle, and then it has a molten iron core, and finally an iron core. Okay, so now let's move on to the system of Saturn. So we only had two missions that really detected oceans. That's the Galileo mission and the Cassini mission. For Saturn, unfortunately, the magnetic dipole is aligned with the rotation axis. So which means that around the moons, there's no real variability in the magnetic field. So magnetic induction is not really possible around for those moons, for the moons of Saturn. So other methods had to be developed. So for Titan, it's really the tidal deformation that really confirmed the existence of a subsurface ocean. And so how does this work? Well, as I said earlier, that when the satellite is closer to the planet, it's stretching more, and when it's farther away from the planet, it's stretching less. So the amount by which, so this is by the way, it's an exaggerated figure, but the amount at which an object stretches back and forth, it really depends on what's inside the object. So it depends on the rigidity of the moon. So if the moon is very rigid, then it will be stretching more, and so the parameter that represents this is the Love number called K2, and so the higher K2 is, the more stretching happens. When there's an ocean beneath the icy layer, then the object will be stretching more. When there's no ocean, it will be stiff and will stretch less, so it will be deforming less. So Titan has relatively high eccentricity, and it's changing distance between apoapse and periapse by about 36,000 kilometers over 16 days. So you would expect to see some tidal deformation in it, depending on what's interior in it. So the method to detect that is by doing gravity flybys. So as Cassini flies near Titan, its orbit gets disturbed. And this shows up in the radio Doppler tracking system. The signal that is sent gets disturbed, and then you would notice it in the Doppler shift of the signal. So the more flybys you do, the more information you can get about the interior of the moon. So you can get, of course, the mass, the shape, in terms of elongation and all, but also you can get information about the periodic deformations. So that's the K2. And so when Cassini flew by Titan and it measured its deformations at different orbital phases, it measured a value of 0.6. So what does that mean? A completely rigid object has a K2 of 0, so it's not deforming at all. A purely liquid body has a K2 of 1.5. A typical satellite with a subsurface ocean has a K2 of about 0.4. So the fact that Titan had such a high K2 number means that it's even higher than for an ocean, which means that definitely there's an ocean, and the fact that it's higher means that it's probably ammonia rich, so the ocean is actually dense, which is good because ammonia is an important element plays as an antifreeze element, so the water can remain liquid to much lower temperatures. The flybys also measured the moment of inertia of Titan, and it found that it's not entirely differentiated, so it's probably the ocean is also like Ganymede. It's trapped between two layers of ice, and then the interior is a mix between ice and rock. Okay, so now let's. I went a little bit fast, but that's okay. Then I'll get to talk about my favorite object. So Enceladus, because it's a small size, an ocean was not really favored in it, because most of the energy that is produced in the rock gets diffused away and then leaves the body, and then the ocean would freeze. So the first hint for something odd going on inside Enceladus was these eruptions from the South Pole that were detected or discovered by the Cassini mission.
Radwan,
Yes.
since you zipped ahead a little bit, did you say how thick the ocean might be on Titan, or do we not have a good handle on that? This one? Like 100 kilometers, is that the depth or the thickness?
That's the depth. So that's the thickness of the ice shell.
Okay.
But I don't think we have a definite number. Alex, you want to add something?
We don't know. It's one of the things we want to try to figure out. It also could vary. There's evidence that it's thinner and perhaps denser up near the poles and thicker up near the crust, near the
Yes.
equator.
Yes.
But most estimates range between as low as 50 kilometers to as high as 120 kilometers.
Okay.
That's the depth again, right? Not
That's the thickness of the ice
thickness
crust.
of the crust. But the
Thickness of the
ocean
crust.
itself, we don't know. We don't have a good handle on how deep the ocean might be.
No, I don't think so, because it depends on the also the density of the ocean and the density of the interior, so it's not obvious.
But if you have an inhomogeneity in the depth of the ocean, then there will be high order moment detection, right?
Yeah, but there's bigger problems right now in that we don't know the density of the ocean, you don't know the makeup of the crust, you don't make makeup of the core. If you have a hydrated core like Jonathan has proposed, you have one scenario. If you have a differentiated core, you have another scenario. And
Okay.
some scenarios will have high pressure ice at the base, some
Okay.
pressures will not. So there's a variety of solutions that you have yet to be.
But just to say something that the thickness of the ice shell, it's very simple to say that it's just a constant thickness all over the object, because it's variable, because you have the tidal stresses that are stronger at the poles, so you may think that it's thinner, which has been suggested for Enceladus, for instance. So all these models are too simplified. You know, the actual ones may actually be more complicated, not only for Titan, but all the other objects.
Maybe just a simple thing. The perturbation to the spacecraft is due to tidal deformation of the satellite, right?
Too many parameters.
So is there how rotational distortion of the Enceladus? Is that negligible?
Well, if you do enough flybys, then you may actually get the orientation of the distortion, because there's always lag. It's not directly pointing at the planet, it's a little bit lagging. But that requires really a high order of gravity, and we didn't acquire this with Cassini.
But I'm talking about rotational bulge, just rotation.
Oh, yes, you get that, yes. So this is where you get the moment of inertia, for example. If you just do one flyby, you may just get information about the mass, for example. If you do more flybys, then you get more information about the shape, so that's the rotational bulge. And then also the tidal bulge as well. So the more you do, the more you get details about the interior or the different parameters. And of course, if you measure the deformation or the tidal bulge at different orbital phases, then you can get this K2, because it will look like as if they are varying as a function of the orbit. So, okay. So the first suggestion for these plumes on Enceladus were that the ice itself is the shear in the ice is sublimating the ice, and it's only ice that is being produced. So it's really happening at the layers, at these fractures. It's really the shearing due to the tides. But then Cassini flew through the plumes of Enceladus, and it detected salts. So in order to have salts in those plumes, it means the salt comes from the rock, right? So in order to have salts in those plumes, the ice has to be in contact with rock. But to pick up this salts, you need to the ice has to be molten, basically. So it needs to be water. So it's the same reason why you have, our oceans are salty, because they're in contact with the rock, while the rivers are not that salty because they didn't have enough time to be in contact with rock, while the ocean has been in contact for a long time. So it's the same thing. So this was the first evidence that suggested that there is water inside the moon. However, because of the same resistance to the idea of a global ocean, what was suggested is that it's only a local ocean, just in the South Pole. And this was confirmed with the gravity data. It detected the mass anomaly in the South Pole. And it's a positive mass anomaly because water has a higher density than ice. So everyone's happy. They're saying, okay, well, that's how the water looks like. And the reason why there's only one is the South Pole, because it's a freezing ocean. And so this is the only place that is left. But then we found that through the libration measurements that it's not a local ocean, it's a global ocean. And this is where I come in with many of my colleagues here at Cornell. So how does the libration work? Just a quick explanation. So for moons that are in synchronous rotation, so they're showing the same face of the planet, when they're on an eccentric orbit, they don't really show the same face to the planet. They actually, as they orbit, they face the empty focus of their orbit. That's the first approximation. So if you place yourself Oh, just before that, and it's the same reason why, for example, we see 60% of our moon, not 50, because the moon is not really looking at Earth, it's looking at the empty focus. So as it's orbiting, you see the different sides of the moon, and you see 60% of it. But that's not related to the interior. This is just purely geometry. Now let's place ourselves on the moon, okay, and looking through toward this axis. So this is how it would look like. So we're standing on the moon, and the moon is the bulge. The tidal bulge is pointing at the antifocus. Because the moon is also changing distance from the antifocus will be going back and forth, while the planet will be going on an ellipse back and forth. But because there's a misalignment between the tidal bulge of the satellite and the planet will create a torque at the satellite. So as a result, the satellite has to respond to that torque, and it will start librating. These are called physical librations. So you'll have, in addition to the optical librations, you have these small oscillations called the physical librations. The physical libration is forced by the satellite's eccentricity, so it depends. The amplitude depends on the eccentricity. The frequency depends on the orbit of the moon, so that's the mean motion. And then you have the mean motion also of the satellite in here, and this is a function of the omega-0, which is the natural frequency. The natural frequency is the whole story. So the natural frequency basically is the reason why this and this sound different. As you excite them, they respond differently to excitation because of what they're made of and because of their sizes. And this is the natural frequency also intervenes in the physical libration. So it depends on the moments of inertia of an object. And so basically, if you have an object with an ocean, the amplitude would be higher than an object without an ocean. And so we went on measuring the surface, or tracking the surface of Enceladus for 7 years with Cassini images. So what we did, we measured points called control points, basically mostly craters. And we tracked those points as they were, with time, as the moon was librating. And when our best fit model, or our best fit libration amplitude, was consistent only with an ocean at a 26 kilometer depth. While all the other models, including the local ocean, were not consistent with our observation. So this was really the smoking gun evidence for the global ocean inside Enceladus. And so more work shows that Enceladus has an icy shell of about 26 kilometers, but in order to be consistent with the gravity measurements that show a mass anomaly in the South Pole, in the South Pole, the ocean is larger. There's more water and less ice, and that's why it shows up in the gravity. The ocean is about 20 to 30 kilometers of thickness, and the rocky core is about 200 kilometers in size. So, how about the future? So, there are two missions.
Can I just jump in there? You said earlier on that Enceladus we expect it to be too small to have an ocean.
Yes.
Except it does. So,
yes.
What are the possible explanations to that?
Yes. So, when first the plumes were observed, the radiogenic heating was the source of energy as radioactive decay was calculated, and it was found it's not enough to melt the ice or to sustain an ocean. Enceladus is in a 2-to-1 resonance with Dione. So Dione is increasing the eccentricity of Enceladus, and so the tidal heating, through tidal heating, it's melting the ice and forming the ocean. However, when you calculate the energy emitted with tides, it's also not enough to produce an ocean. So really you have to bring in the dissipation inside the planet, in this case. So what's happening is that because there's dissipation inside Saturn, it's the dissipation inside the planets basically are the reason why moons are moving away from the planet. And so what's happening is that the planet is pushing the satellite further inside the resonance, because Dione and Enceladus are not in perfect resonance; they're a little bit off. And so what happens is that the planet pushes the satellite further inside the resonance. The eccentricity is increased. Tides decrease this eccentricity. So the resulting eccentricity you're seeing now is called equilibrium eccentricity. It's the eccentricity after producing a lot of heat and toning it down a little bit. So the answer is really is in the dissipation of Saturn, where we found that the dissipation in Saturn is actually 10 times larger than previously expected by the model. So, but it's a complicated discussions, and we can have it after.
So what does that mean for the age of the ocean?
This depends on the age of the moons. So it depends on when Enceladus was caught in resonance. The problem with forming oceans is that tides alone cannot form oceans. You need at least a thin layer of water, and then tides can just keep sustaining it and makes the ocean larger. So this means that there probably has been an ocean before with other resonances, and probably with the initial radiogenic heating that was stronger in the past. And so I would suspect that the ocean has been here for a very long time, but that's just my opinion. So long time, that's billions of years. But it's just my opinion and my speculation. So I don't have a model that I developed.
So this equilibrium eccentricity you talked about, it's the same idea that has been talked about for Io for a long time, right? That Io is also thought to be in such a equilibrium with Jupiter, right?
Well, yes, but it's believed that Io is moving inwards, so it's heating so much that its semi-major axis is decreasing, so it's moving inside. So for Io, it will leave the resonance with Europa, and then it will cool down, and then it will start migrating out again, and then it will get caught again in the resonance. So it's a back and forth relation or history for Io.
But it's in a different phase of the cycle, perhaps, than Enceladus.
In what sense?
It's in a different phase of that cycle if it's moving out of the resonance.
Yes, it's not
rather
in
than
equilibrium.
moving.
It's actually beyond equilibrium. It's actually making it move inward.
Yeah.
So it's too much heat produced in Io. So Io is not a candidate for an ocean unless you can swim in magma. That's so how about the future? Currently, we have two missions that are being built. JUICE to go. Both of them are going to the Galilean system. JUICE is planned to be launched sometime around 2020, and is planned to arrive in 2030. Is planned to enter an orbit around Ganymede in 2030. But before that, it will study other moons of Jupiter. We also have the Europa Clipper. We have people here at Cornell that are involved in this mission. And I'm not sure about the dates because I really didn't find any concrete information. Do you have any information about the dates, Alex?
The target is launching around 2022, and that depends on the status of SLS, and its arrival very much depends on the status of SLS.
Okay, so we don't really know the arrival date. Okay, so what's good about these missions, they have better equipment. Everything is more modern. So we'll have better magnetometers, which will allow us to have better information about the size of the oceans inside those moons. We have better cameras, which will allow us to have measurements of the libration of those moons, especially Ganymede and Europa. Also, the camera and the laser altimeter will allow us to have very good information about the topography, which is topography basically linked to the interior and all the convection or geophysical processes happening beneath. And so we also have there will be a tracking system, and since JUICE will be around Ganymede, we'll have very good information about the interior. So I think with those two missions, we'll have very good information about the interior, or what I call an overkill. So how about more in the future? How about other potential missions? So the object that is still left out is Triton. And this is a moon of Neptune. It has an eccentricity of very low. I don't know if I had enough zeros, but it's very low eccentricity, which means that any tidal dissipation is not going on there. But it has a very high rocky fraction, so most of its heat is being produced from the rock, from the radioactive decay. You wouldn't expect to be able to measure to any tidal deformations nor librations. However, Neptune has its magnetic dipole that is here it's 47 degrees tilted from the rotational axis, which means that if you actually fly by Triton, if there's an ocean inside, it will be very easily detectable through magnetic induction. So currently there are ideas of missions to be sent to the ice giants, and I think Triton would be one of the best candidates to have an ocean. So let me conclude with 2 slides. The first one is, we all know of this idea of the habitable zone where water can remain in its liquid state so that life can develop. If you're too close, then it's too hot and water will evaporate. If you're too far, then it's too cold and water will freeze and life cannot sustain or develop. And then there's us, who struggle in keeping Earth habitable. But space exploration has taught us something, that even you're outside of the habitable zone, you can still find habitable islands where other sources of energy than the sun can form water and probably form life. I would like to finish with this slide that shows, to our best knowledge, the volumes of oceans inside those icy satellites. So this is normalized to the volume of oceans on Earth. So 1 means it's the same volume as Earth, 5 means 5 times larger. So just think about that for a second. There's 5 times, or there's more water, except for Enceladus, there's more water on these icy satellites than on Earth. So imagine if we only understand or only know about 10% of life in our own oceans. Imagine how life could evolve or develop in an ocean that is 5 times larger than the oceans on Earth. So I believe that finding life in those moons should be a priority, or one of the priorities in the future space exploration. Finding life in those moons will confirm that life can exist beyond Earth. And it will mostly confirm the existence of life beyond Earth, but it will also open the doors very wide to limitless possibilities of life, of extraterrestrial life, in our solar system or in extra solar systems. Thank you very much.
Thank you very much. Great talk. Questions?
Yes.
Can you do this vibration test on the other Saturnian satellites? Can you look for the same, can you find high points on the other moons to see?
Yes, so this is one of the works I did on Mimas. And Mimas, actually the first application for libration was not on Enceladus, it was on Mimas. And we also found that it's librating much stronger than just an oceanless moon. And so one of the suggestions, one of the interpretations for Mimas was that it may have an ocean. However, Mimas is pretty boring on surface. It doesn't have any resurfacing, so it's difficult for it to have an ocean, so it's confusing, but you can do that. Beyond there, it really depends on the eccentricity. So Dione, you may be able to measure the libration of Dione, but it's a little bit challenging and you have to have very sophisticated softwares, but I think it is doable. For Tethys and Mimas both, since they are an inclination type resonance, which it means that they have obliquities, and you may be able to measure their obliquities instead of librations. Beyond that point, Titan is actually a very good object to have a measurable libration. However, for Titan, you don't really have very good observable surface with cameras. You only need the radar.
If we had an orbiter at Uranus, are any of the moons close enough in order to do this kind of study?
So for the Uranian moons, I don't know what are the eccentricities for the Uranian moons, but I would doubt that there's any ocean in those moons, just because of their. Actually, let me go back all the way to one of the first slides. So the rock, the silicate fraction in those moons, most of all the uranium, they have a low rock fraction, silicate fraction, and they have small sizes. So,
But Enceladus.
So Enceladus, as I said, it's really tidal heating. So for the Uranian moons, none of them are in resonances, so they're not expected to be having any tidal heating. So if any moon would be a good candidate for having an ocean, it would be Triton. That's around that.
I would be careful, though. You never know what you're going to find when you get there.
Well-
Because Miranda is around Uranus, and explain that.
I thought it was suggested that it was an old ocean that froze and expanded it that formed those coronae. But I agree with you that space exploration has always proved us wrong. And but that's just from the models, this is what we can predict.
So maybe this is an engineering question, but it might be hard to get into orbit around the ice giants. And so there are also a class of missions encountering flyby geometries. And so how close to Triton would you have to get with your magnetometer in a flyby configuration to identify the ocean?
Oh gosh, I'm not an engineer, I'm not a magnetometer guy, but I think the fact that the magnetic field of Neptune is varying so much, I think the signal will be much stronger for Triton than for Europa or for the Galilean system. So I think it can be detectable from farther away than what Galileo did for the icy moons. But I really don't have numbers. So.
Richard.
What about the possibility that life was invented more than once on the Earth?
That life, say again?
That life was appeared more than once on the Earth. You would detect that by the chirality of the clouds.
Well, that's always a possibility that life. But I don't know how can you confirm that, or Phil, you're the archaeologist here. Can you?
As far as I know, there's only evidence for one formation of life on Earth, but yes, you could find biochemical evidence that there was multiple ones, but we're a little bit far. That requires actual sampling of the life forms.
Yes, and this is actually an interesting idea. For example, if you had those icy satellites that maybe the ocean froze at some point, then it entered into a resonance, and then it melted again. So it's an interesting idea, actually. Yes.
So, one up. Oh, sorry.
No.
So, do you have a good explanation for the north-south asymmetry on Enceladus with the ocean?
I do. Well, I'm saying this because this is my work. Actually, what I have suggested, me and my team, we suggested that we found evidence on the moon that the Enceladus had true polar wander, so it's changed axis. So this hot spot was not actually in the South Pole in the past; it was actually somewhere else. So we speculate that what caused this. So when we look at the topography, and so we suggest that this hot spot was actually in the leading hemisphere of Enceladus. So what we suggest is that probably there was an impact that caused this mass anomaly, and then this impact, because if it's a mass anomaly, it caused the whole moon to reorient and place this anomaly in the South Pole. After that, since this anomaly was in the South Pole, the tides were strong enough to keep it warm and molten. But so because it's already weak, the tides are the stresses are stronger in the South Pole than the North Pole. So this is one of the ideas that's been suggested for the asymmetry.
Maybe just follow up. How large the polar wander from the
We suggested that it's a 55 degrees reorientation of the axis. So yeah.
the tidal effect on the Enceladus due to planet realign it to the.
So the true polar wander idea we had is that because, well, you need a mass anomaly in those moons to reorient them. Because if it's a mass anomaly, then it won't be in equilibrium. So it has to reorient to place this anomaly to make the body, to place the North Pole to make it aligned with the highest moment of inertia. So that's what happened. Because it was a mass anomaly, the largest moment of inertia was not aligned with the pole. So it had to reorient to bring back the equilibrium.
So,
Alex,
okay,
go ahead.
I guess your thoughts on, so when I think of Dawn's discoveries at Ceres and looking at widespread what looks like remnants of widespread serpentinization reactions, so that there was liquid water interacting with silicate rock in the past that's now frozen. Does that mean that all your bodies under that line are places where there probably were oceans early on in their history, and that affects their evolution subsequently, and that when you're talking about oceans, you're merely talking about oceans existing today?
Yes, it's oceans existing today, because what we care about is the survival of the ocean over the timescale of the solar system. So these bodies, because they have a small silicate fraction, of course most of the heating was happening earlier in the solar system, especially with the presence of the aluminum-26. So I believe all of those, I mean I can't just say all of them, but I believe many of them had oceans in the past, and as the decay energy, or the amount of energy produced by radiogenic heating decreased, then the oceans started freezing, and then they completely froze. And so now all the energy that is produced from the rocky interior is basically, because of their small size, it's being diffused away directly, and the ocean cannot really sustain. So yes, I'm talking about oceans today.
Phil.
So handy you put that slide up again, because I was going to ask about Pluto, which is lurking over on the left there.
Yes.
Now granted, it's not very good for hunting for oceans because it's in a synchronous orbit and it's a circular orbit and it's not sitting around a planet that has a magnetic field. So none of your diagnostics are sort of available, but do we see any evidence, do you think, from the New Horizons data that there could be an ocean on Pluto now, or is it not being talked about?
Well, I think definitely that the surface, the activity on the surface is a good sign that there's something is going on inside. I think the shape of Pluto, this work has been done by Francis Dimo. I can't remember because I heard the talk like when New Horizon got there. But I think from the shape, he concludes that there is a global ocean inside. But it's not, it's not smoking gun evidence like other detections. So yes, Pluto is a very difficult case to unravel its ocean. What I think the best way to find ocean
It's a binary, right? It's a binary.
Yes.
It's a binary.
Yeah, but it's tidally
What's the
evolved
eccentricity?
and becomes
What's the
synchronous.
What's the eccentricity of that?
Zero.
Zero?
Zero.
Now, but even if it had eccentricity, you need the torques from the central planets to make the librations or to make the deformation, and there's no really central planet. I mean, it is
The other one.
It's Saturn,
yeah.
but Saturn is very small mass, so the deformations will be very small, or the libration will be small, so because the torque is too small. So I think the best way to find an ocean in Pluto is finding an ocean in Triton, because Triton there are similar objects. Triton is believed to be an object that was captured because it's on a retrograde orbit. So Triton is believed to be a Kuiper-Belt object, and it doesn't have an eccentricity, and the only source of heating on Triton is the radioactive decay. So because they share the same origin, I would suspect that Triton and Pluto would be similar in terms of existence of ocean.
Although Triton could have received a large impulse of energy during the capture event.
Yes, so the fact that Triton has such a small eccentricity, and whenever an object is captured, it has a high eccentricity, so it had to go through tidal heating at some point and to damp this eccentricity. But since now it's zero, whatever heat that was produced from the tides, now it's gone. So any ocean or extra layer of water that was formed from the tides, now it has frozen back again to its original size. So.
Last question, okay.
I was going to ask, is there any evidence of differential rotation between the crust and core of these objects? Is that a hard thing to answer?
So since those objects are in synchronous rotation, so they're facing,
Okay, they all are.
right? But they're still vibrating, right? Theoretically, you would expect that the rocky core would be vibrating at a different phase. So it would be really like these going back and forth independently, because if you have an ocean, they're separated from each other. So there's no evidence, but theoretically they should be doing that.
Okay, so Radwan is local, so I'm sure he would welcome everybody interested in his office in coming days, weeks, months. Let's thank Radwan again.